Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Well, good morning, everybody. It's a pleasure for me to introduce Christian Richard. He's a PhD student at the University of Cambridge. His advisor is Neil Dodson. His research interests are in stereo and non-photorealistic rendering.
Thank you very much for the introduction. So today I'd like to talk about two pieces of recent work that both relate to coherent depth in stereo vision. And they're taking slightly different views. So the first part is going to be about how to extract coherent stereo maps from disparity maps from stereo videos. And the second part is going to be about how we as humans perceive coherent depth from stereo images and what causes viewing discomfort in these images. So the first part is joint work with Douglas Orr, Ian Davis, Antonio Cremonesi at Microsoft Research in Cambridge, and my advisor. And the second part is joint work with Les Shriersky, Ian Davis, and again my advisor. So starting with the first part of the work, our work was motivated by adaptive support weights, which is a very popular local stereo matching technique that produces good results, but it's also very slow. Takes about 1 minute for the Tsukuba stereo image. And our aim was to speed this up by several orders of magnitude, and this is to make it practical for real-time use, and hence make it fast enough so that coherent stereo matching from videos could be looked into. So to briefly describe this, what they've done is for computing the support weight of a particular disparity hypothesis at a pixel, they consider the distance between pixels in space as well as in color, and use an exponential fall-off. So the pixels that are further away in terms of distance within the support window, for example, pixels in the corner, receive a lower weight, and also pixels that are different in color, like those pixels that are not actually on the orange lamp, also receive a lower support weight. And the aggregated support space, so summing over all pixels and then normalizing again, looks very much like a bilateral filter. So we've reformulated their technique as a bilateral filter using Gaussian weights instead of these exponential weights. And the result is what we call a dual cross-bilateral cost aggregation, because the cost aggregation happens with both stereo images in mind, and color differences in both stereo images are considered. So these are the first two Gaussian weights, and then there's the distance weight as well, but it's only considered once instead of squared, as in the case of Yon and Kwon. So we found that this produces slightly better results on almost all cases in our implementation. But now that we reformulated this as a bilateral filter, the bilateral filter also is very slow. So we looked into different techniques of how to accelerating this aggregation approach, and we used the bilateral grid to approximate the aggregation. And what we achieved is more than 200 times speed up on compared to the full kernel implementation, and this is more than 30 frames per second on all Middlebury datasets. And the way it works, roughly outlined, is that the original signal is embedded in a higher dimensional space and subsampled. This space is then smoothed, and then the signal is sliced again out of it so that it's filtered. So it's an approximation of the bilateral filter that works very well for large standard deviations, which is the case in our approach. And here are some disparity maps for comparison. So this is the original adaptive support weights by Yoon and Kwon in our implementation. It ranks about halfway down the Middlebury stereo evaluation website, and the runtime for the cones image was about 14 seconds on a GPU. After our reformulation, the rank is slightly improved. The runtime is increased a little more because the computation is a bit more expensive. But after the speed up, some of the quality has been lost. This is because now the stereo matching happens in grayscale only, and is an approximation to the full kernel bilateral filter. So the rank is reduced a bit, but the runtime is improved by 180 times. So now it's actually very fast to run this. And at the time of publication, at ECCV 2010 last year, this was the fastest stereo matching technique in the Middlebury website. Now, these artifacts are obviously very undesirable. So we investigated ways of reducing these artifacts, and we came up with a dichromatic approach. So we used an additional color distance to get some of the discriminability back into our approach. The problem is that the bilateral grid has exponential memory requirements in terms of the number of dimensions. So only one extra dimension could be accommodated in the memory on the graphics card. So we analyzed a few different ones, and interestingly, we came up that the U is the most discriminative by only a slight margin over the others that we considered. But what it does restore is, for example, these sticks, which are very similar in the grayscale image. It does restore them, and it also removes some of the artifacts of the lampshade compared to the bookcase in the background.
Question. I'm not sure if this would work, but couldn't you run your cost aggregation, your support window, on all 3 color channels or LAB or something like that, and then just add them together so you don't take this exponential blow up? In other words, run 3 sort of grayscale problems and then just merge them.
Well, that sounds very interesting. So it would have to be run 3 times, and then you could presumably work. That's very interesting, yeah.
I mean, you'd have to think about how the costs get added, you know, what it means. So you want to do a multiplication or an addition or something like that, but basically there's some evidence in each of the 3 color channels, whichever space you choose to use. Or 2 in this case, but at least you didn't tell us what the time is here, but I presume it.
Yeah, sorry, I glossed over this. So the interesting thing was that this dichromatic approach is halfway in terms of performance as well as runtime between the full kernel approach and the grayscale only DCB grid approach.
So halfway means that instead of getting a 200 times reduction, you get
It's only 1 order of magnitude faster than the full kernel. So yeah, halfway in kind of logarithmic space.
Okay, so that's not bad. Whereas if you just ran the problem 3 times in 3 color channels, it'd be three times slower. 2 times slower.
I think so, yeah.
Okay.
Didn't actually consider this. An additional application that we looked into is spatial depth super resolution, and this was a paper by Yangadal in 2007, and they used Uniquant's aggregation approach to create high resolution disparity maps from low resolution disparity maps and high resolution stereo input images. But their technique essentially uses Uniquant as a single step. So where Yangadal used Uniquant's technique, you can also use our technique as just slotting it in. And the improvement is that it's more than 100 times faster. But again, you lose just a little bit of quality in all these cases, but this might be a desirable trade-off in some cases. But making the stereo matching so fast makes it possible to look into kind of incorporating temporal evidence, because if you apply stereo correspondence techniques on a per frame basis only, then it is likely to flicker. Because videos are noisy and they can result in different disparity values over time. So our approach is inspired by space-time stereo approaches, where we add another time dimension to our support window. Now have a spatial-temporal support window, where we consider 5 frames and add a Gaussian fall-off over time. And the result of this is visible in these videos. You can put on your anaglyph glasses. The top videos are shown in anaglyph, so you might be able to see them. And the bottom 2 videos show disparity maps, the middle one for per frame approach, and the bottom one for our temporal approach. And you can see that the flickering is reduced, particularly in the sky region for the skydiving video. But some limitations still persist, like a disparity in low weakly textured areas are very difficult to compute accurately using local stereo matching technique. So these are some qualitative results, but for these videos, no disparity maps are available, ground truth disparity maps are available, and we couldn't find any videos with ground truth disparity maps available, so we decided to create our own using Blender, and we created these 5 videos. We'll hopefully start playing at some point, yes. So they show they show very simple objects, because we are not really good modelers, but they show different different motions. So for example, an object rotating, or object motion, or panning across the street, or moving around in this tunnel.
So these disparity maps are incredibly high quality, right? Is that because you didn't edit
They're actually rendered directly from the depth buffer.
Oh, That's not the output. This is the ground truth images.
Yeah, sorry, these are the ground truths.
Okay,
Yeah.
no problem. Great.
Too many videos. Sorry, that was one too far. I'll just go back. Okay, so here you can see the results of our techniques. The ground truth on the bottom left, and the DCP grid produces a fairly good result there. Also copes well with the slanted surface, even though the aggregation approach only assumes a frontal parallel plane approach. In our temporal technique, you can see that it doesn't improve much or at all over the per frame approach, and this is because these videos are kind of the perfect case for stereo matching. There's no noise in them. It's ideal for stereo matching. So in the next step, we actually added some Gaussian noise to model this, and in this case, our temporal technique improves quite a bit above the per frame technique, and also the original ionic one approach and even our full kernel reformulation show quite a few artifacts. So some of the spatial subsampling that happens in the bilateral grid seems to also produce some better results in the end. So this is for the books video, and then also for this video.
Look, I mean, the amount of noise is higher than you normally expect, but there's also something fishy about how badly Unit 1 is falling apart. I mean, there's always a tunable parameter. It's somewhere inside every stereo algorithm. There's a tunable parameter that adapts for noise, and it kind of seems like you didn't quite set that one right.
So we actually ran this on different noise levels, and across our 5 videos, in most of the videos, our temporal approach improves on the per frame approach quite noticeably in terms of the proportion of bad pixels. So just to sum this up again, we rewrote the adaptive support rates as a dual cross bilateral aggregation filter, and this enabled it to be accelerated using the bilateral grid, so making it more than 200 times faster compared to a full kernel implementation at only a kind of a small loss of precision. And this is so that we could incorporate the temporal evidence into the stereo matching process in real time. Source code and datasets are all available on the project website. So this marks the end of the first part. Are there any questions on this part so far? Yes, please.
Do you have any insights why change on those kernel and that will improve the performance, or what type of data will improve?
I don't have any insights so far on that, unfortunately. I believe that using a Gaussian fall-off, so quadratic exponential, gives more weight to local pixels so that are more closer rather than the single exponential fall-off. So that under the assumption that similar colors produce similar disparities, the support window is then tightened up a little bit. But the improvement is only very small compared to the adaptive support rate technique. Okay. So the second part is more recent work that was presented at Computation Aesthetics 2 weeks ago before SIGGRAPH. And this is work that is trying to predict viewing comfort of stereoscopic imagery. So the problem is that the visual comfort in stereoscopic imagery is very subjective, if not subconscious. And it's an issue in visual perception. And assessment of this has traditionally been done by expert viewers or a panel of naive viewers. So this is in the context of a stereoscopic movie production, for example, where every day the produced content would be shown in a cinema on site, so they can check that the stereo is correct and doesn't introduce any discomfort. And this assessment is very time-consuming and also very costly. So our goal is to provide an objective assessment of this visual comfort. And to do that, we rely on a computational model of the human visual system and analyze how a range of image manipulations, in our case Photoshop filters, influence the viewing comfort. So there are many sources of discomfort when looking at stereoscopic imagery on displays or on screens. And this part is only concerned with image discrepancy, so differences between the two stereo input images. But there's also a range of other issues that affect visual comfort, and they could be related to the physiology of vision, so the separation of the eyes, for example, but also the particular display device and display technology used. So everything but the first one is assumed to be constant for the purpose of this work. So our model consists of 3 stages. And the first stage starts with the input images, the left and right input images, and applies an optical blur to mimic the optical properties of the human eye. So this blur is very small and removes high frequency details. The second step computes disparity maps using normalized cross correlation. So the disparity maps are computed from left to right and from right to left, and the consistency of these disparity maps is then checked using the left-right check. And this map, where white pixels indicate inconsistent areas, is then summarized into a single coherent score that describes the proportion of pixels that are considered to be consistent or coherent between the 2 views. And these are all the black pixels here. But let me go into more detail about all these stages. So the first stage uses a weighted sum of 2 Gaussians to mimic the optical blur of the eye. And this has been described by Geisler and Davila and measured for a particular scenario, the well-focused eye 3 millimeter pupil, and also based on the assumption that 1 pixel in the image corresponds to 0.6 arc minutes of visual arc, which roughly corresponds to the spacing between foveal cones. So this is what the point spread function looks like. So there's 1 larger Gaussian and 1 smaller Gaussian in the middle. The second step uses normalized cross-correlation, which has been proposed as a model of human stereopsis, so human stereo vision, by Banks et al., and has been refined by Filippini Banks, 2009. I'm just trying to explain normalized cross-correlation without showing the formula. So I think some of you will know very well how this works, but I will still try to describe this using images. So starting from the input images, we apply the optical blur. So the blur has now been applied. Fine detail, fine high frequencies have been removed, and the model also works in grayscale. So now, from now on, everything is in grayscale. So for particular pixel and particular disparity hypothesis, 2 windows are considered in the 2 views, and these windows are first normalized, zero mean normalized. Sure.
You're describing the Banks model here,
Yes.
and you're saying it works in grayscale.
This is what my reading is.
No, that's fine. I haven't read it, but does that? If you make that assumption, does that mean that those of us who actually see the Tsukuba, the things pop out like the pencil pop out, are somehow abnormal? Because in grayscale, we can see that there is no difference between the, the pencil and the background, right?
That's a very interesting point. So this is actually work in the visual perception literature, and they only consider grayscale random dot stereograms, so they had no color component. So this is why I use the model as is. But yes.
Well, different reason. Just send an email to Marty Banks and ask him, do you truly believe that the system only works in luminance, and therefore, if we have an isoluminant stereo display, I mean, we know, I think in general, a lot of perceptual systems in the isoluminant case don't work particularly well. Okay. But, has he quantified this? Maybe there are follow-up papers or something like that. So
it's very interesting.
They just sort of, it jumped out at me. It's not about your work; it's about his, because you had just showed us how the color makes a difference, right, in the performance.
Yes, but this is also then resulting in limitation of our particular approach here as well, that color differences in the images are not considered. If they're isoluminant, then they will not show up as issues. So after normalizing these patches, they're multiplied together on a per pixel basis. And what Filippini Banks improved on, contributed on top of this, is to apply apply a Gaussian falloff to mimic the cortical receptive fields. So again, the pixels further away are given a lower weight. And this is now averaged together, all the values of all the pixels, and this results in the correlation score. Yes, and this correlation score of about 0.4 is fairly low, but this is done for all disparity hypotheses, and the highest score, in this case is 0.9, is then considered to be the disparity with the highest correlation score is then taken to be the disparity at this particular pixel. So it's a very simple stereo matching technique in terms of stereo vision literature, but it's very interesting that it correlates very well with human stereo vision. And the third step of our model checks the consistency of the disparity maps. So it identifies inconsistent pixels, because disparity maps from left to right and from right to left should show roughly the same view. So corresponding pixels should, the disparities of corresponding pixels should sum to 0, and if they don't, they're considered to be inconsistent. Okay, so this is, these are the 3 steps of our model. We start with the input images, compute the 2 disparity maps, and then compare the consistency and sum it up using a single coherence score. And this score is necessarily between 0 and 100%. And our hypothesis was that this score correlates with the human comfort ratings. So to evaluate this, we ran a perceptual study using 20 participants, and we showed them 80 stereo images each on our passive polarized stereo display.
So
Yes?
it's independent on the size of the disparity? Shouldn't it be dependent on the size of the disparity, because that relates to the comfort level, right?
Yes, for the particular stimuli that we showed, the disparity are all in very similar ranges and in a fairly comfortable range. Excessive disparities is one of the sources of discomfort that are listed in the beginning, and we're not looking into excessive, assessing the impact of excessive disparities.
But what are you really assessing in this case? It seems like that's, like, for example, disocclusion or something like that is a big factor that will, in your model, make something uncomfortable because you then can't match.
Yeah, this is definitely one of the limitations, and it's a limitation in our model. Because the stereo matching technique is very simple, it has these limitations, it has these issues in occlusion areas. I'm showing some examples later on of this. So we showed these stereo images on our stereo display using passive polarized glasses for everything in color, not in anaglyph like here. And we asked our participants to rate their visual comfort, how comfortable they perceived this particular image that we showed on this 5-point Likert scale between very uncomfortable and very comfortable. And the 80 images we showed are composed of 4 original images. So 3 images, you can use your glasses again for this. 3 images from the Middlebury data sets, so this Books, Mobius, and Teddy. And then we also created one rendered one ourselves of a city model. And all of these have been edited so that most of the content is behind the screen plane, so it's more comfortable to look at. So this is also to kind of counterbalance with some of the other sources of discomfort. And all the anaglyph images in this part are shown in grayscale as to reduce further the discomfort that you would see if they were actually in full color. But all these images that we showed are actually in color. So we showed these 4 original images, and for each image we applied 19 Photoshop filters, and also showed the original image so to compare relative to how much a particular filter influenced viewing comfort. And these 19 Photoshop filters applied to the original image. So for example here the city image. And this should be, out of all the effects, should be the most comfortable because it's just rendered straightforward, there's no inconsistencies there. But for example the charcoal effect should still look fine, but one issue is that these light and dark strokes actually have kind of slightly random lengths, so they're not very consistent across the 2 views. But it should not be too much.
Apply the effects independently?
Independently to both images, exactly. So originally we considered implementing a range of non-photosynthetic rendering techniques, but then used Photoshop filters instead because they implement a much larger range of image manipulations like segmentations and thresholding and all kinds of things. And in fact, we actually looked at a larger set of Photoshop filters, 51 filters first, and then identified these 19 to show them to a larger range of people. Another example is this glass style. So this displaces pixels in both views, but it displaces them consistently. So what it actually looks like is that as if you're looking through a glass plane. And this is known as a shower door effect, and I will also use this term later on. But in comparison, this ocean ripple effect applies different displacements to the 2 views. So it is quite difficult to actually fuse the 2 views. And this is one of the most uncomfortable images that we had in our data set, according to human ratings. And there's also, well, there are actually 2 more examples. So this is photocopy effect. And it works surprisingly well, in my opinion, because it just extracts high frequencies. It's like an edge detector, essentially, but it's very coherent. It works very, very well. And as the last example, this texturizer effect applies some texture to both views the same. So it's like looking through this slightly translucent layer onto the scene. And we analyzed our 1600 human comfort ratings, first using correlation to find out how it relates to our model ratings, and we found that our model is as good as any particular participant. So the correlation between pairs of participants is the same as the correlation between our model and any participant. So this is the first conclusion we arrived at, and the other one is that our model overall correlates strongly with the mean rating. So taking the ratings of all 20 participants and averaging that together, because that is more indicative of how the average human feels about stereo content rather than how any particular individual feels about the images presented. But we were also interested in looking at how our model, where it differs from the human perception. So we rescaled our coherence scores, which are between 0 and 100%, into the same range as the human comfort ratings, between 1 and 5 on the Likert scale, using this least squares fit. And using this fit, our model predicts 70 out of 80 images to within 1 unit of comfort. And in this histogram, you can see the distribution of the difference between the predicted and the human comfort ratings. And most of them are centered at around 0 difference, which is very good. But there are also some outliers. And for example, these 5 outliers on the positive end, where our model overestimates visual comfort, they are due to the shower door effect, which I showed earlier to you some examples. And it seems that our model can tolerate this much better than human observers can. And on the other end, where our model underestimates visual comfort, these effects rely largely on noise, and the human visual system has evolved to be very tolerant to small levels of noise, whereas our model seems to be more brittle in that area.
I'm wondering why you assume that the score scales linearly.
For the correlation, I didn't actually assume that it scores linearly. This was just the simplest fit I could think of, and the fit was actually worked pretty well. So, but all the statistical data and is available on our project website. So I would be interested in finding maybe there's some more to be found there in the data. Before running this perceptual study, like I mentioned before, we actually looked at a larger set of images using 6 input images and 51 Photoshop filters. So we looked through all these 306 images with 2 viewers, and we looked at, tried to identify the issues that we saw in these stereo images. And we found that there were only 3 major issues in our data set. And they are due to binocular rivalry, the shower door effect, and also randomness in the images. I'm going to describe what we mean by these 3 categories, each with small examples and also showing some example images later. So retinal rivalry is due to alternations in perception due to mismatched stimuli. So in this particular example, you should see vertical lines in one eye and horizontal lines in the other eye. And this is a stimulus that cannot be fused because it's not physically possible. And what you should see instead is that one eye dominates for a few seconds. So you see, for example, horizontal lines. And after a few seconds, the other eye will dominate. And then you will see vertical lines instead. And this is this crops up whenever there's strongly conflicting image regions between the stereo half images, and the range of effects that can cause this, for example, segmentation or morphological operators or color quantization, because all of these can influence the boundary of objects, and they can be modified differently in both views and not necessarily consistently. And one particularly strong example of this is the palette knife effect, where large areas of color are applied, and there are quite a few areas of retinal rivalry.
I'm wondering if you've done any experiments where you keep the left image constant and you do something to the right image. Like, for example, compress the right image or have a different resolution, effective resolution, and so on.
I think there's been work that did that. Also work that considered a wide range of different manipulations as well, like blur or vertical disparities or compression, and they looked into that.
Right. Just to verify whether your model holds in those situations.
It's interesting. I will look into that, yeah. I can run that on this data. I haven't actually tried this, I only applied it on images that are manipulated identically in both views. The second category in our taxonomy of stereo issues is the shower door effect. And this is a term used in non-photorealistic rendering literature and describes the effect as if you're looking through some frosted glass. So here there's some lines behind the screen, and these dots, they're on the screen plane. And they actually detract and make it quite difficult to fuse the lines in the background. And the easiest example is if a texture is composited into both stereo images, because that results identically into both stereo images, because that results in a zero disparity plane that is directly on the screen, and then you have to kind of look through that before you can see the actual content of the scene. And the example that I showed before was this glass effect. But in general, the shadow effect doesn't have to be in front of the content. It could also be behind. If there's some content that actually comes out of the screen in terms of disparity, then the shadow effect on top would actually contradict the depth cues, and this would be even more uncomfortable than looking through this layer of glass. And the third category identified was randomness, and this is the catch-all category that applies whenever the same effect applied twice to an image produces different results. But they mentioned before, the human visual system is actually quite good at tolerating small levels of noise. It's just when there's more noise, like these wiggly lines that are wiggling differently in the both views, that they're difficult to fuse, which makes it uncomfortable. And the simplest example of this is per pixel noise, like this film grain effect. I can actually see it quite well here. But it should still be possible to fuse that quite well, because noise is ignored quite well by the human visual system. Well, building on this, we were also wondering how we could actually detect and localize these issues in the images. So we came up with a set of computational tools. And the rivalry is already largely there with using the left-right consistency check map, because it flags up the inconsistent pixels. The only thing we then do is apply a Gaussian blur, again, to mimic receptive fields. And here you can see these white areas are the inconsistent areas, and these are the occlusion areas in this example, because it's the original input image and there shouldn't be any inconsistencies. So the score given to this image is something like 84%, not 100%, as you would expect in a perfect model. It's also similar on this particular style. But on the palette knife effect that I showed earlier, the large areas of inconsistencies that are flagged up. And in particular on the stained glass effect, which is very inconsistent because it uses different Voronoi tessellations in the two views. It's really difficult to fuse that, and rivalry is flagged up throughout the entire image. This was in fact also the most uncomfortable image we had in our dataset. The second issue we identified was the shadow effect. And we built a detector that uses likely disparities, which are locally maximal, which have locally maximal correlation instead of globally maximal. And this is because the shadow effect will still show up as a local maximum in the disparity in the correlation, but it will not be the strongest. In most cases, it will not be the strongest correlation score, because the background, the actual scene, usually results in a larger correlation score. So we identify all likely disparities in all pixels and then accumulate them in a histogram throughout the entire image. And this is the histogram shown here. And for the original image, nothing is flagged up. Similarly for this cutout effect. But the glass effect that I showed earlier has a very strong peak at zero disparity. So our detector notices that there's something floating in front of the scene. Many pixels have like a disparity of 0, which indicates that there's something in front of the scene. And also particularly strongly in the texturizer case, where a texture is composited identically into both images. And for randomness, we compare the color of corresponding pixels. And this is only of corresponding consistent pixels. So if the color is too different, then this is considered to be, well, if it's above some just noticeable difference. So in this example here, in this case, it's scaled so that black is 0, just noticeable differences, and white is 2. So any light colors should result in, are due to inconsistencies between the two images on a very fine scale. The cutout effect also looks largely fine. Some of these artifacts are due to the lack of texture in areas which local stereo techniques are not very good at handling. But for this reticulation style, there's quite a bit of randomness between the two images because these blobs are placed randomly. So a lot of that is flagged up, and in particular for the film grain effect, where there's a lot of per pixel noise, inconsistencies are seen throughout the image. So in summary, I described the first computational model for predicting the visual comfort of stereoscopic imagery. And this is ideal for automatic assessment of visual comfort without without the need for costly and lengthy perceptual studies. And we can see this wherever an artist would edit stereo content and kind of as a small tool on the side that would analyze the content created just there and would flag up areas that needed further attention. We also introduced the taxonomy of stereo coherence issues and tools to detect and localize these issues. And the project website contains all the images that we showed to our participants, as well as their ratings and our statistical analysis. And before I wrap up, let me use this opportunity to say that I'm looking for a postdoc position or something similar from spring next year. Thank you very much for your attention.
Comment on the second part. How do you actually see it being used? I mean, is this for Photoshop or spec designers? Like how?
This is the particular approach we used because just as a proxy for different techniques. I actually see this could be useful for any content because it doesn't rely on having the original images available. So it's not an image quality metric which would compare how the disparity maps are deteriorated by applying a modification. It actually you can actually use it on just content that you have, and you could conceivably use this, for example, for stereoscopic image editing, where you could then retarget your disparities or ensure that effects apply to certain areas, like that use noise, are less prevalent or made more consistent.
You could use it for when they make 3D movies to give the cinematography of the people editing some feedback to create scenes.
Yeah.
I mean, there are inconsistencies in just, right? I mean, you have occlusion, you have specularity, you have all sorts of other things, right? So,
yes.
And it's just yeah. It just seems.
Also, for videos, you would have to consider how the coherence changes over time. So it's not just per frame, as in this case. We just do it on single images.
I mean, if I was a Photoshop effect designer, I would actually take the ground truth disparities that come with a bunch of images and actually apply effects to those and use that as my correlation to see if this is going to give me something that's consistent, rather than doing normalized cross-correlation. Now, normalized cross-correlation is good for images which you don't have any depth for it, you're just doing some random shoot. But then you need some sort of baseline. And it's just, if you look over the whole, I guess you could look at it as a specific part that you're editing.
Yeah, it could apply to just a small window too.
Yeah. Then you would need, whenever you do the editing, you're going to need your. It just seems unclear how it's being incorporated into somebody who's actually working on a stereo movie per se, trying to manipulate it and how this will get used.
Could, for example, be also used in post-production when you edit both images independently for compositing effects onto something. Make sure that the presentation in stereo is then comfortable.
Do people do that though? Don't they generally render something in 3D and render it in
I think there's a lot of manual work involved as well. There are lots of digital artists who actually edit images by hand, paint mats, for example, by hand. And obviously, if you can render it and create it in stereo, then this is preferable because then it's most likely to be consistent. Yeah.
I have a question. Typically, in most stereo pairs, you have semi-visible regions due to occlusions, right? And would this model predict that those cause discomfort?
In the current incarnation, it does, yes.
Okay.
So this is a limitation of the model. So one of the items of future work that we had is that using a stereometric technique with occlusion handling, or using a global stereometric technique would likely improve.
It's a limitation. Is it possible that people just find it uncomfortable to see those semi-fused regions?
Yeah, I've been wondering about that, but I haven't arrived at a conclusion yet, really. Okay. I think the human brain has some mechanisms for coping with this, because we see occlusion every day, really.
Right. Right. I mean, it's hard to say without running an actual test, right? But we see them every day, but if we sort of stare intently at a region which has a semi-occluded region, something seems a little flat or strange, right? So this is something you could investigate, right?
Sure.
And I mean, ultimately, you know, people who care about this work are people who are producing, let's say, stereo movies, and they want to minimize fatigue and things like that, right? So that might be an interesting question to look at.
On stereo movies, so how would you extend your work to video? Because that's probably more important, right? And there are other cues that has to be taken into consideration.
I think that there's some might be some masking that comes into effect as well if things move, if objects move very fast, or depth perception also deteriorates in that case. So it may not be very necessary for that. But I don't have any direct ideas of how to extend this to video for now. But I think it would be the most promising approach is to actually model the stereo coherence between the views as well as the temporal coherence in kind of one frame, right? Rather than having independent components, because I don't think this is actually orthogonal to each other. It's actually influences each other.
It may be possible that the score is pretty low on a single frame, but when you play as a video, it may look okay. Any other questions? Well, if not, let's thank the speaker once more.